3. Так. Ні. We'll be back. Jeez. You guys, how much you guys? 2 more minutes. Oh, welcome to viewers online. So, language students. I don't teach language. And oh, hello, hello. Okay, maybe it's time to start.
3 minutes away already. 3 minutes past the time.
No one.
No. Not how. Okay. Let's do it. What's in my point for today? What I'm trying to teach today? We saw very nice tool for deal with non-harmonic currents. It's a Fourier transform. Fourier transform is a useful instrument, but there is one serious limitation in this part what we do know. What kind of limitation? Classic Fourier transform requires signal to be periodic. It's written on the base of periodic function. And what if my signal is not periodic? Example. I like this example. T0. This is my output voltage. What will be output voltage? What about circuits theory? Capacitor discharge. Silence. capacitor discharge always looks like this. It will be 8 power of time constant. Alpha here 1. You can check multiple processes and many processes behave like this. Decaying exponent or growing exponent. It's one of the basic things of this world. It's a determined continuous signal, but it's not non-periodic. No, it's a non-periodic or aperiodic signal. And now a question. Can I get Fourier transform, kind of Fourier decomposition for such kind of signal? Can I find a way somehow from signal in time somewhere get its representation in a frequency space? Classical Fourier transform substitutes periodic signal. What in reality, what this box represents? If you look deeper, classical Fourier rule represents periodic signal as a function of k omega or double P. It's a discrete frequency function. It's only determined. What I got here? Base frequency, second harmonic, third, fifth. This is second, third, fourth, fifth, second. Signal represented here scales and angles. As something, if you look deep, what's this something in function of? It's base frequency, double, triple, and so on. You will see discrete frequency function. There is no 1.5, 1.3, or 2.4 frequencies. Base, double, triple, quadruple, and so on. Okay. And what about non-periodic signal? Analysis in frequency space is easy. It's definite. But how can I get my signal in frequency space? I can start with the sequence of pulses. In theory, what can I do? Here is my discharge of one capacitor, single. In theory, I can cut some piece, say what it's one period, and attempt to perform, for example, do a DFT with it. On this part, what will be the result? I will get some set of C and S, fine. But this set represents not this signal. This set represents sequence. If I simply cut piece from original signal and perform a DFT on it, I will get Fourier transform, but this transform will be for sequence. It will repeat in real world. I can do a brute force trick. I can do discrete Fourier transform, perform calculus, and forcibly I can do kind of simulation, and cut. See, if we take a strong march, this tail is infinite. In reality, I can find approximately where time period where 90 or 95% of energy concentrates. And I can forcibly cut simulation at this border. So, inside will be 90 or 95% of energy. I will abandon tail. It's like cut like this. And abandon this tail. Ignore it. In life of brute force solutions, this is possible. But it's very dangerous sometimes. Because for such, how to say, regular decaying, easy foreseeable signals, it will work. But if, for example, you try this for PWM converter, there is PWM. Modern electronics, modern power electronics, often has a spectrum like sine x divided by x. It goes with wave. And cutting simulation forcibly is dangerous. I can omit part what causes an AMC problems. They have quite long tails and energy, how to say, hills. It's in frequency space, it looks like, and one of these tail hills can cause serious problem. So, simple forcible cut simulation may be dangerous. Okay. I will not cut simulation. I will try to dig deeper to get correct mass for this. What I have here, it's a sequence.
Yeah.
My schematic at this moment, I have a generator producing pulses of 1 microsecond, 1.9. Okay, 1.9. Pulses of 1 microsecond with what I have period 1.3 kilohertz E equal to 1 divided by 1.3 kilohertz. Generator producing pulse. Capacitor of 1 nanofarad and a resistance 100,000 ohms. And here is my yellow signal. If someone would see, here is my capacitance box. Now it's set for 1 nanofarad and 10,000 ohms resistance. Nice box. Resulting voltage. At each pulse, capacitor charges and discharges through this. It's not a box, it's a barrel. And discharges to a resistance barrel. So here are my set of exponential pulses. Yep. Each pulse is a power minus half t, yeah? And they are coming with a period of t capital. Let's say 1 pulse. Here is my pulse generator. Slept well?
Sorry.
Come here. With non-periodic signals. I have a pulse generator powering a RC network. One microsecond pulse of 5 volts charges this capacitor box, and then it discharges to 100,000 ohm. It's not a box, it's a barrel. Campbell Brothers, number 104. So I have this sequence of discharges. Sequence.
Capacitor is discharged?
Yeah, every. What will be 1 divided by 1.3? 1 second. 1 dividing by 1.3. Approximately 0.8 millisecond. So, actually, each division of scale, each tick is 200 microseconds. So, each approximately 0.8 millisecond, capacitor charges and then discharges through resistance. Next pulse arrives, again charges.
This graph of the capacitor, yeah, I think.
Yeah.
It's a voltage of capacitor. Again, schematics. Pulse generator, capacitor, resistance, and yellow line, my signal. Look, I will change what I'm changing. Period of the sequence.
Like you are changing this one. That's
I'm changing
in this circle, yeah?
this period. Yeah, this means this going up. What happens? Oh. No period found. Come back. Periodic 667. Oh, no period found. What happens? This is periodic signal. It has frequency. non-periodic, periodic, non-periodic, periodic, non-periodic. What happens?
Professor, as I understood, this period is too long. Capacitor, like when capacitor full and it blocks.
Nope. Nope. I can add a second scope, if you like. This one, for example. Come here. Don't worry. And I only need, what I need second wire. One moment. Wires. We need more wires. More wires. We got wires. It has two outlets, so I can. Where is second, which is ground, which is hot. I think like this. Escaping yields capacitance. Right here. Where is my balls?
Professor, they are making this circuit, yeah?
Where are the right? I would like to get pulses invisible in analog scope. Something. Where is my should see.
Well,
I should
I
see.
guess you're gonna stay with me.
I should see. Nice.
You guys need my You need my
Come
well,
If everything. Oh. Yeah. Here I see. Nice. It's an actor. Yeah. This is charging pulse. 1 microsecond. This is nice charging pulse. What's prevented? What's prevented to appear here?
So let me understand this. Can you tell me which one is this capacitor, which is resistor?
This one is capacitor. It's a box, and this one tens 100,000 ohms barrel.
Okay. What about this one right now? This is
It's an oscilloscope.
yeah.
I would like to see here. If it works correctly, I should see. Here are you. Here is my pulse. Here is my little. Here they are. Everything nice except one problem. Here they are so tiny. No, this scope is not up to task to show them. You see, they're like nails. Not. Maybe here they are like thin nails. Maybe this one will be better. Second. I need. Stay here.
Professor, after you finish, let me ask you one question.
Just I'll catch my pulses. Pulses, I'm catching. something connected here. No, I want.
So can I see or you want me to do something?
Yeah. Now what all this about? Inside the car. I use single output. Single isn't very much better. I can connect. You stop running. Charging pulses. It's a charging pulses at bull line. Each now 2 microseconds. This one is 2 microseconds. Within 2 microseconds, capacitor charges,
Yes.
and then discharges through the this resistance barrel.
Yeah, so the period of capacitor, like charging, discharging, is even less than this period.
The period of this sequence
Yeah.
here, and it's set by the pulse frequency. It repeats itself. Yeah. Here you can see it repeats with each charging pulse. And period. Or like this. 200, 400, 600, 800 microseconds. So 2 microseconds within after each 800 microseconds. Capacitor charges and then discharges freely. Now, I'm increasing. What I'm changing?
Here.
Period. I'm increasing period, decreasing frequency. No period found. Why no period found? Did pulse disappear? Here, scope sees only one.
Yes. Identify the periods and master 2.
And what about what's here? Here there, 1, 2, 3. It's very narrow. divisible 1, 2, 3, 4 within. What's going on? For my scope, time begins here. It's a 0 time. And at this point, memory ends. It's a digital scope. It shows what's inside a memory. For my scope, end of time is at this line. Time ends here. After this point, scope sees nothing. Memory ends. Table ends. My imaginary students write table of values. Table ends, signal ends, because not written. Signal itself exists, but we don't have any information about it. For scope, here is the end of time. Periodic, non-periodic. Periodic, non-periodic. So, if I shift this next one after the border of visibility, no one sees it. And if no one sees it, observable part of the sequence will be non-periodic. Yeah? Understand this trick? Or don't? I'm thinking on shifting period towards infinity. My white line. So, I have one pulse. Oh. I'm creating a sequence. Okay, I'm creating a sequence. Let's see. The m from minus infinity to infinity. I can do like this. Here, m is simply integer. I will create what I will create. It's exists. Sequence I can perform a Fourier transform on it. I can get complex curve. It will be 2 divided by L, starting from L by R. A power minus J car time this K. Oh. Now I'm increasing period to infinity. When for my scope, you see, next one somewhere here. But scope don't see it, so it's non-periodic signal. if I shift period to infinity, when the next pulse will happen? After the doomsday. No one cares about it. Previous, before world was created. So, no pulses. Only. See what happens. To infinity of my sequence is only one original pulse. Next one shifts after the doomsday, no one observes it. Previous, before world creation, no one observes. The only observable part of the sequence remains this pulse. Globally, I can, in mass terms, I can do the same trick I done with my scope. Shift next one, to happen after observable time. Fine. This means what harmonic value of omega k is 2 divided by half minus infinity to infinity minus infinity power minus your omega k. Here omega k is k double p divided by period. Nice formula, but what will be limit of this? Zero.
Zero.
So appears what it is useless formula.
I think.
This part remains. I can use it. More common form of Fourier transform deals with thing called spectral function. It's a spectral function. If classical Fourier transform of periodic signal produces spectrum, here we have spectral function minus infinity to infinity, my pulse, a power minus omega time in time. Spectral function is a complex function of frequency. Spectral function is something abstract. It is not performable in our space. Classical Fourier rule consists of real harmonic signals. Spectral function is absolutely abstract. It's a complex function and it do not exist in this world. Okay, but what's the usage of abstract function not realizable, not performable here in this world? It's a brain play. This function is usable. How? Remember idea of transfer function. If I have circuit with input and output, what can be represented as a complex frequency function. Yeah? remember my 4 circuits. Capacitor, resistor, and coil resistor. Yeah? Remember first circuit? If input is a spectral function, transfer function asks for something being function of frequency. Yeah? If input is a function of frequency, it's okay? It's okay. What will be output? Output will be spectral function being multiplication of input function by transfer. Analysis in frequency space is easy. The only problem is what I will get as a result. Spectral function, yeah? Something imaginary, complex. I have one problem. I need to convert spectral function into time function. I need an inverse Fourier transform. Result of analysis will be imaginary spectral function. If I can, see? If I have something, let's say Sx, I can say what spectral function of x is a Fourier transform of Sx. Sx is non-periodic signal. Output Sy will be inverse Fourier transform of output spectral function. Only problem, where is my inverse Fourier transform? Direct transform formula I just wrote. Become periodic. Make my life easy. Any ideas where to run? No ideas.
Sorry.
How to get this?
You mean inverse Fourier?
Yeah. Of course no idea.
I think it must be same with forward Fourier transform. Only thing that we have to like change is instead of dt we're gonna use dv. Yeah.
First, it should, yeah. I feel what it should be something integral. It should be in frequent space, omega. V is work. Omega, Greek, is frequency.
Yeah.
What can it be? We will try. 1 second, maybe I can. Fourier transform, time to inverse u. Time to do something. At first, one remark on spectral function. See what the moment is. If I have, let's say, I have a signal, periodic. The period is less than infinity. I can obtain spectral function of it. So let's imagine guy S is a result of Fourier transform on this signal. No problem. What will be value of harmonic coefficients? Easy. AK will be harmonic at a frequency k double p by time, or 2 divided by period value of spectral function at a frequency k double p. So we can, if we have non-infinite period, we can get classical Fourier law. It's one of the ways to perform inverse transform. I can set period, simulation time within a period and get Fourier law. I need to set period long enough. For example, if here everything's ends 1, 2, 3, 4, 5, let's say in 10, it's mean 2 milliseconds. If I set simulation time for 2 milliseconds and obtain and assume it's a period, I can create a Fourier law for periodic signal with period of 2 milliseconds. And within 2 milliseconds, spectral function will give me values of harmonics. It's a brute force approach, but it works. And now, let's go a bit deeper. So values of spectral function are complex harmonic factors for classical Fourier law. But can we get strongly defined mass explanation? I will write everything what I know. So signal was set as sum of my pulses. It's possible to substitute it with the Fourier law. A power J E double P where Fourier law coefficients can be taken or substitute with values of spectral function. So it will be 1 by half multiplied by period by half, sum from minus infinity to infinity, let's say on a power J here it is. Sum of pulses substituted with Fourier rule and AK taken as a values of spectral function. So no omegas is a Fourier transform of nice? And now let's do the trick. Let's shift period to infinity. Oh, period shift to infinity. Limit where period shift to infinity of n to infinity equals to my original pulse. Original pulse yellow. Now, we need to take a look on what? 1 divided by period, sum starts from minus infinity to infinity. Spectral function of f power j p. We need to take a look what will happen with this nice sum, where period goes to infinity. There is one moment. Remember spectral diagram? We saw, for example, for my rectangles, what was spectral diagram? 1 at 1 omega time nothing at 2, 33% at 3 omega, and so on. What's the space between lines in spectral diagram? What's the step of scale? It's one frequency or double P so step between next and previous frequency is double P divided by period. Yeah? Correct? What's omega is k double p divided by t. Fine. What can I write here? I can write what it's equal to 1 divided by p something. We start from minus infinity to infinity. Values of spectral function frequency omega k, power j omega, and multiplied by this is space or distance between spectral lines. If period goes towards infinity, when the space between spectral line goes. Once more. Spectrum, this space is double p divided by period. Where it goes? To 0. All spectral lines come together. And what we will get? One nice area or figure. This sum will become what? Integral. Okay. So, limit of the sum will be integral in minus infinity margins. I will get something like 1 divided by double p integrate from omega f power j omega z omega. This means what at the end of time, it will be from minus infinity to infinity omega e power j omega d omega. Here is my inverse Fourier transform. Oops. For non-periodic signal, I, with help of this nice situation, I can get reverse, I can get my result back. Now, why? Where are we? We have again our circuit. I have pulse generator, no, it's 2 microseconds, and with repetition period. The capacitor box, resistance, okay, it's my signal. What being sum of all what's a mass for this one? This pulse is A minus alpha when time is greater than 0 and 0 when time is less than 0. Here, alpha time constant is 1 against Rc. Need Fourier transform. Spectral function Fourier transform. My pulse will be, I need to integrate from minus infinity to infinity, a power j omega time in time. What will I get? Equals to E, in my case 5 volts, 0 to infinity, A minus alpha, A power omega time d time. So it will bring me E divided alpha plus omega. Here is spectral function. So spectral function for my signal is E divided alpha plus j omega. Yes. To make it easier, I can what can I do? I can represent it as a magnitude and angle. So magnitude will be E divided by square root alpha square plus frequency square A power minus arc tangents tan omega divided by alpha. I can draw magnitude. It will be something like this. 1 per u at 0 and 1/2 corresponds to double alpha. 1/2 is approximate minus double alpha. Can I make it more visual? I can do one thing. I can go the full cycle. I can choose some repetition period. For this, I will get a Fourier row double divided by period multiply a divided square root of alpha square plus double p square a power minus your arc tangents got double p divided by period divided by alpha. Push the button. You go here. And I will get a red line here. Maybe okay, this is fine. My scope, what I'm doing. My scope is smart enough to perform a discrete time Fourier transform. Happens. Red line is a result of discrete Fourier transform from yellow line. Each peak is a value of a k. 0, k1, k2, k3, k4, and so on. Space between them is double p divided by this period. Here is chart. What I will do, I look, I'm changing period twice. Now period is 2 times shorter. And what do we see? Do you see what happens with space between lines?
Yes, yes.
It's doubles. The higher time between pulses, the closer is spectral line. At when only one remains, here should be uninterrupted area. The closer pulses, the higher is the gap between spectral line. It's number one. Understand why? In strong mass, because here is division by period. Next one. My new capacitor box, new old capacitor box. I will change, look what happens. I'm decreasing capacitance. I'm increasing capacitance. The higher capacitance, the higher is inertia. The higher inertia, slower change. 1 second, I will get it like this. Now I can, okay. I will double. I'm doubling the capacitance. Capacitance increases twice. That means what? Alpha time, see? Rate of change changes twice.
Yeah.
And what happens with spectral lines?
Increases.
The, maybe, wait 1 second. I will bit compress the spectrum. I'm changing alpha twice. See what happens with tail. With this tailing. Alpha decreases, rate of change increases, and spectrum becomes wider. Maybe this to make change sharp. I'm changing 6 times. It's approximately, no, 7. Sorry. I'm changing alpha 7 times. Slow, sharp, slow, sharp. See when the tail of spectrum is. The sharper change, the longer spectrum. Spacing, do spacing between. What's defined spacing between spectral line? This time a repetition. So, lines do not shift, but the tail ends here. Now only 100 picofarads. Now capacitance only 100 picofarads. Maybe 1 second. I will bring my resistance box. Resistance box and switch. 1 second. Switch, where are you? Here is my resistance box. It's for 100,000 ohms. I will connect it in series. I will connect it in yeah. Now resistance is 200 kilo ohms. And switch to wires. I need a pair of wires. This will go. This will go here. And red one should go one second, I'll draw schematics. This. Pulse generator, capacitance, 100 car, 50 car, 50 kilo ohm. This is my signal, and I have switch here. I'm changing alpha 4 times. To make it see where the tail of spectrum is. Slow change, short spectrum. Fast change, here spectrum ends. So the fast change means wide spectrum. Slow change means short frequency area. Where is my? I should appear here. Fast change, long spectrum. Slow change, short spectrum. Here how it is. So first, the higher distance between pulses in time, the shorter space between spectral line. Point 1, point 2. Our conclusion. The faster rate of change of pulse means longer spectrum. Slow change, short spectrum. It's very important when you deal with power electronics. The fast rate of change means more high frequency components. More high frequency components, shorter life of semiconductors. It's reality. That's why sometimes snubber networks are introduced. RC networks connected in parallel to suppress high frequency components.
So fast change in pulse it leads to long spectrum.
It means what it has, long spectrum means what it has more high frequency components. Long spectrum for yellow line, X is a time, for red line, it's a frequency. Red line is a function of frequency. It's a result of Fourier transform. Oh, I erased my formula. Red line is a values of spectral function at a frequency set by frequency of my black generator. Spectral function is abstract, but if it's okay for us to have non-infinite period, we can get Fourier rule as a values of spectral function. Tiny pulses. Okay, questions? Maybe online some questions. Fast change, wide spectrum. Slow change, narrow. If I say short, oops. Very fast change. Much slower. And you see, energy concentrates in low frequency area. This rapid changes, and you see the energy, all the tailing goals, they are relatively small, but they go for long. This means what you will, in case of such very fast changes, you will probably face an AMC problem, electromagnetic compatibility, because this high frequency component will interfere with radio broadcasting, TV, with your systems, digital brains, and so on. Design well your power electronics part. Let's number network. Slow changes, short spectrum, no AMC problems. Okay, appears what time is out for today. Questions? Last chance. Okay. If no questions, I officially declare do not write with coaxial cable. It's coax for it has a wave resistance of 75 ohms, and it's for TV broadcasting. It's for